to the colloquium, everybody. So I'm very pleased to introduce today's speaker, Shahar Dobzinski. Shahar is a faculty member at Weizmann in the Applied Math and Computer Science department. He works in various areas in game theory, including mechanism design and other areas. His thesis at the University of Jerusalem won the Outstanding PhD Thesis Award. He's also received multiple Best Paper Awards at EC. And he's going to be talking about non-recent advances in today's talk. So yeah, Shahar, please go ahead.
Thanks. Okay, yeah. So I initially thought about talking about recent results, and then I figure out why not talk about non-recent results? No need to to always discuss the most recent results. So this talk is going to basically take the flavor of a survey. I'm going to tell you about results that we have obtained over the years, and regarding how to prove the complexity of incentive compatible mechanisms. Now, toward the end of the talk, I will touch a little bit about more recent results, but mostly it's not going to be like very recent ones. Okay, let's start. I'm going to talk about two different settings in this talk. One is combinatorial auctions, and the other one is multi-unit auctions. They are quite similar. In combinatorial auctions, we have a set M of heterogeneous items and N bidders. Each bidder I has a non-decreasing valuation function that gives a value for every possible subset of the item. So this valuation function allows us to capture things such as, suppose that a chair is a value of 10 for me, and a table is a value of 15. Together, the value is 50 because they consist of a set together. We will sometimes assume all kind of restrictions on the valuation function, some modularity or subadditivity. The exact definitions are not very important for this talk. The other setting that we're going to discuss is multi-unit auctions, which is quite similar. In a multi-unit auction, we have M identical items. So items are all the same and N bidders. So this is exactly the same setting, except that I only care about the number of items that I get. Okay. I get 10 items. It's every set of 10 items has the same value for me. So here I care only about the number of items that I get, not about the identity of these items. Okay, so that's the difference between the two settings. And please do ask questions throughout the talk. Okay, so now we want to define good mechanisms for these settings. I'll focus here on multi-unit auctions in this slide because other settings are similar, maybe with different numbers. So what is a good mechanism for multi-unit auction? So I'm a computer scientist, and the first thing I want from a good mechanism, I want it to be fast. Okay, I want it to run quickly. Here I will think about fast algorithms as algorithms in which their communication complexity is polynomial in n and log m. N is the number of bidders. Log m is the number of bits that I need to write down the number of items that I have. Okay, so this is going to be fast algorithms for me. Of course, just saying that the algorithm is fast is not enough for us. We have like all kind of silly algorithms, like the algorithm that never allocates any items to the players. It's very fast, but it doesn't do anything useful. So I somehow need to rule out this algorithm. And we'll do it by asking that the algorithm will provide a good approximation to the welfare. The welfare is simply the sum of the values of the bidder. So I want to find allocations that will give each bidder some number of items, such that the total happiness, the total values is as large as possible. Now, I cannot find the exact solution in polynomial time. This is by an easy reduction from the knapsack problem. So recall that in the knapsack problem, we have n objects. Each has a size Si and a value Vi, and we have some total capacity M. The goal is to find a maximum value of subset of the object with total size at most M. So how can we translate the knapsack problem to multi-unit auction? We'll just take each object in the knapsack problem and make it a player in the multi-unit auction that wants Si items. And if he gets Si items or more, then the value of this bidder is going to be Vi. If he gets less than Si items, then the value is 0. And we're going to have M items overall. And you can see that, if we can find a good solution to multi-unit auctions, then of course we can also find a good solution to the knapsack problem. And this gives us in particular that finding the optimal solution with multi-unit auctions is hard. Okay, so we have this. Okay. Now we can approximate the knapsack problem quite well. We can get an FP test, 1 plus epsilon approximation, and turns out that these algorithms generalize quite easily to multi-unit auctions as well. So we can get a 1.01 approximation to the welfare for multi-unit auction. Okay. Now this talk is going to be about game theory. We want to think about a situation where the players are strategic, so we cannot just hope that they will just tell us what their valuation is, because they might want to manipulate the algorithm in order to get more items to increase their happiness. So we also want to have the requirement that the mechanisms that we design are incentive compatible. What does it mean? It means that the value of each player is private. Only the player knows its value. And we're going to charge some prices from the player. Each player will maximize his profit, the value of the items that he got minus the price that he has to get. And we'll aim for algorithms that each player can maximize their profit. If you're not familiar with this concept, then I guess the most well-known example is the one of a second price auction. So in a second price auction, we have just one item, not M items, just one item. Each player makes a bid. The winner is the one with the highest bid, and he pays the second highest bid. And it is not hard to see that the dominant strategy of each bidder, the best thing that each bidder can do, is to simply bid his value. Okay, and that way it just maximizes his profit. So we're aiming for a generalization of this simple second price auction from one item to many items, and we also want it to be fast and to provide a good approximation. Now, if we don't care about the algorithm being fast, we have this celebrated VCG mechanism. I will explain what it is later. This VCG mechanism finds the optimal allocation in polynomial time and is also incentive compatible. Unfortunately, it does not run in polynomial time. So the main question that we're interested in this talk, and one of the many questions in algorithmic mechanism design, is whether we have something that is in the intersection of all these three circles. Whether we have an algorithm that is both fast, is incentive compatible, and provides a good approximation. As you can see right now, we have, for every two circles, we have an algorithm that has both properties, but we don't have yet an algorithm that combines all these three circles together. We don't know if this intersection is empty or not.
So if we allowed ourselves running time which is polynomial in M, then we could just run VCG.
Say it again, please. I'll just increase the volume.
Allowed ourselves running time polynomial in M rather than log M.
Yeah, I mean, in combinatorial auctions, we care about algorithms that are polynomial in M. Here, the right thing to do is logarithmic in M, simply because, for example, the approximation algorithm running time that is logarithmic in M. So if I'll now allow you to run in time that is polynomial in M, that's I'll giving you exponential power more than what I can do in what I can do as usual. So basically, the question is whether we have fast algorithms that provide a good approximation. Can we have algorithm with the same complexities that are also incentive compatible? Okay, so that's why I'm focusing on algorithms that are polynomial in N and logarithmic in M. Does that make sense? Okay. Yeah, for combinatorial auction, we'll just do the same thing with N and M, and so the issues are really similar. All right. So let me tell you about the plan for this talk. We're going to talk about methods for constructing computationally efficient and incentive compatible mechanisms. That's going to be the short part of this talk. Unfortunately, we don't have that many ways of constructing mechanisms. And most of this talk I'm going to spend on proving impossibilities. How we can prove impossibilities for computationally efficient incentive compatible mechanisms. So, but we'll start with some positive results, and then we'll try to prove that these positive results are actually optimal. That's the plan. Okay, I promised to tell you about the VCG mechanism. Recall the VCG mechanism provides the optimal location for multi-induction in polynomial time. For multi-induction and is incentive compatible, and it is not polynomial time. The VCG mechanism is actually more general than this, as we will see now, but we will just see the application of the VCG mechanism for multi-induction. But similar ideas apply for essentially every other setting. So what is the VCG mechanism? First, you find the welfare maximizing allocation O1 to On. So bidder 1 gets O1 items, bidder 2 gets O2 items, bidder 3 gets O3 items, and so on. So we assign the bidders items accordingly. And then we're going to pay each bidder I the sum of the values of all other bidders. This is a bit annoying because we would like to think about the mechanism as charges payment from the bidders and not paying to the bidders. We can fix it by introducing a suitable constant. This is not going to change anything, but to make our life a little bit easier for now, let's just think about us paying the bidders for getting the items. And the focus is going to be on proving that this is still incentive compatible. Okay, this constant is not going to change it. So why is this VCG mechanism incentive compatible? The proof is actually quite simple, just in this slide. Let's prove that it's incentive compatible. So let's look at the profit of each bidder. And I claim that the profit of each bidder equals the welfare of the allocation that we obtained. For example, let's look at bidder 1 profit. It is composed of 2 terms. One is the number of items that he gets. He gets O1 items, so his value is V1 O1, plus the payment that he got. The payments that he got is the sum of the values of all other bidders. So if we sum these 2 terms together, we get that the total profit of bidder 1 and of any other bidder is just the welfare maximizing allocation. Okay. So now a bidder can try to manipulate the algorithm and maybe try to misreport his valuation, report some other things. What will happen in this case? This bidder might cause the allocation to change, but to change to an allocation that is suboptimal, that has less welfare than the optimal allocation. And since the profit of the bidder equals to the welfare of the allocation that's obtained, the bidder has just decreased his profit. So we shouldn't do that. Does that make sense?
Yeah.
Okay. Question? No. Okay. Good. So this is like a really nice idea. So, the obvious next question that you should ask is, okay, we can't find the optimal location in polynomial time for multi-unit auctions for many other settings that we care about. So why not just, plug in some approximation algorithm and use VCG payments, pay each bidder the value of the other bidders in that allocation and get some incentive compatible algorithm. And the question is that in general, this is not going to get us an incentive compatible algorithm if we just use a generic approximation algorithm. In fact, this is going to give us an incentive compatible algorithm only if the approximation algorithm is of very special type, is maximal in range. So I'm going to tell you what the definition of maximal in range now, and we're going to see an example for this in the next slide in case it's hard to understand what is a maximal in range algorithm. So a maximal in range algorithm is simply an algorithm which a priori restricts the set of all possible allocation. So, we just get rid of some of the allocation. We focus on some limited set. But on this limited set, you always find the best allocation. Okay? So instead of looking on the full set of allocation, you just get rid of some allocations. And, but you always find the best allocation in that specific limited set. Let's see an example for a maximizing range algorithm that will hopefully clarify matters. And this example will also give us a true approximation for multi-unit auction, and it goes as follows. We're going to split the items into n square bundles. Each of them is going to have a size of m over n square. Then we're going to find the welfare maximizing allocation O1 to On with respect to the bundle. So the size of each O1, On here is going to be a multiple of m over n squared. Okay, so we just bundle the items into big sets and find the optimal allocation with these big sets. We assign the bidders items accordingly, and then we're going to pay each bidder I the sum of the values of all other bidders, minus a suitable constant that we're going to ignore here. Okay, so is the algorithm clear? We just, instead of allocating each item to the right place, we just bundle them together. We're going to have much less bundles now, but we're going to allocate these much less bundles optimally. So that's basically the idea. And the theorem is that this mechanism is incentive compatible, uses small communication, and provides a true approximation to the optimal welfare. So let's see that. Okay, so incentive compatibility, the algorithm is maximal in range, so it's also incentive compatible. So again, we're going to find the optimal location where each bidder gets, where the number of items that each bidder gets is a multiple of m over n squared. A bidder can try to manipulate the algorithm and misreport his valuation. The only thing that he might achieve is to change the allocation to one that is going to be suboptimal in the range. So the profit of this bidder can only decrease. So that's why this algorithm is incentive compatible if you use VCG payments. As for the running time, this is just a simple dynamic programming solves it. The point is that now the number of big items that we have is much smaller, just n square. So it's easy to find the optimal location right now, just standard dynamic programming. And I'm going to prove you the approximation ratio that this algorithm provides a true approximation to the optimal welfare in the next slide. Okay. So the key claim is that there exists an allocation in the range that holds at least half of the value of the welfare maximizing allocation. And since we are optimizing over all allocations in the range, we are guaranteed to get at least half of the value of the optimal allocation. The proof is quite easy. First, we're going to assume, without loss of generality, that all items are allocated. So we're going to look at the solution O1 to On where all items are allocated. If there are some unallocated items in the optimal solution, just allocate them, I don't know, to bidder 1. That's fine because the valuations are monotone. So we can allocate items to bidder 1. So we have that, since we have m items in general and n bidders and all items are allocated, we can assume that, say, the first bidders get in the optimal solution at least m over n items. We're going to call this bidder big if the value of this bidder in the optimal solution is greater than the sum of all other bidders. And now we're going to have two easy cases. In the first case, the first case is when bidder 1 is big. That is, the value of this bidder is more than the value of all other bidders together. In this case, we can just allocate all items to bidder 1 and get to approximation. Okay. This bidder anyway is contributing the optimal solution half of the value. If we just allocate all items to this bidder, then this bidder is going to get a multiple of m over n squared. So this allocation is in the range and provides a true approximation, which is what we wanted to prove. The other case is when this bidder is not big, when this bidder is small. In this case, what we can do is we can round up each OI to the nearest multiple of m over n squared and allocate no items at all to bidder 1. Okay, so this allocation provides a true approximation because each of bidders 2 to n got more items than what he got in the optimal solution. and they together contribute more than half of the value in the optimal solution. So this allocation gives us a two approximation. We constructed the allocation such that each bidder gets a multiple of m over n square items, right? Because we just run it up to the nearest multiple of m over n square or run it down to 0. So this allocation is in the range, except that we have to prove that we haven't allocated too many items. Right? So let's see why this allocation is feasible, why the total number of items that we allocated is at most m. So notice that as for bidders 2 to n, each of them got at most m over n square items compared to what they got in the optimal solution. So m over n squared times n gives us a total of m over n additional items that were allocated to bidders 2 to n. But we remove these m over n items from bidder 1 that we initially assumed get at least m over n items in the optimal solution. So what we actually did is we took m over n items from bidder 1 and distributed them among bidders 2 to n. Okay. So that we now can be sure that we didn't allocate more than m items. So the approximation ratio is 2 in this case. Each bidder gets a multiple of m over n square items. We didn't allocate too many items. So this means that in each of these cases, there is an allocation that is in the range. Since we have a maximum in range algorithm, we are guaranteed to find an allocation that has at least half of the value of the optimal solution and is in the range in any case. Okay, does it make sense? Okay. Okay, can we get better than this? We said that we can get 1.01 approximation if we ignore incentive constraints. The conjecture is that no. I think that this algorithm is tight. So if we have an incentive compatible algorithm that provides a better than 2 approximation, then I conjecture that it uses exponentially more communication. And this situation is similar to other cases. We have a simple maximum range that is provides the state-of-the-art approximation. We conjecture that this simple algorithm is optimal, but we don't know about any non-trivial impossibility. So this is similar to what we have in general. And this leads us to the second part of this talk when I'll try to tell you a bit about techniques for proving these impossibility results for polynomial time incentive compatible mechanisms. We're going to talk about 3 different techniques. And we're going to start with one that we're going to call the characterize and optimize approach. Okay, so what is this approach? The idea is to divide the task of proving an impossibility into 2 steps. One is completely about game theory, and the other one is solely focusing on the computer science perspective. The game theoretic step is a characterization step. It says something that I want to prove that every multi-unit auction mechanism is maximal in range. Okay, that by restricting myself to maximal in range mechanisms, I don't lose that much. This is inspired by an old result called Robert's theorem. And Robert's theorem tells us that if we have an unrestricted domain, that is, think about allocations, but I care about what the other bidders care, and and the valuations are not necessarily monotone. So if I get more items, my value might go down. So if I don't have any restrictions about the valuation functions, and I output at least 3 different alternatives, then the set of a possible incentive compatible mechanism consists only of maximal in range mechanism. That's the only thing that I can do. Okay, so that we know. The problem is that this theorem does not scale down to more restricted domain like multi-unit auctions or combinatorial auctions, where I care only about the items that I get, where the valuations are monotone, and so on and so forth. Okay, but this is inspired by this Robert theorem. So this is the first step, the characterization. We want to say that all possible mechanisms are in fact maximal in range. And the second step is the computer science kind of step. This is the optimization step, where we say, okay, if all mechanisms that we care about are maximal in range. Let's just prove the impossibility for this set. And for example, in multi-unit auctions, we know how to do this step. We know to prove that every maximal in range mechanism for multi-unit auction that provides the 2 minus epsilon approximation uses a lot of communication. So this means that if instead of dividing the the set of bundles to bundles of size m over n square, I will divide them to bundles of size m over n to the n cube or something like this, this is not going to help me. Every possible partition of the items, it's still not going to give me a better than 2 approximation in polynomial time. So this is the optimization step. We know to do the optimization step for multi-unit auctions, but as you can guess, we don't know how to do it. We don't know how to do the characterization step for multi-unit auction. We don't know to prove that the set of all possible mechanisms is maximal in range. Let's see some other success stories for the characterized and optimized approach. So, we have a long list here that I'm not going to go over, but what is important to take from this list is that the characterization step, we don't really know how to do. We know how to do it only for restricted settings, but we are quite good in doing the optimization step. If we restrict ourselves to maximal range mechanisms, then we can prove like impossibility result. The hard part is to prove that the only thing that we care about is maximal range mechanism. Okay, does that make sense? Let's dive a little bit deeper into this thing. And if we look at the success stories, we can see that the domains in which we managed to prove the characterization result are domains in which, let me call them for now, Roberts domains. These are the results in which the set of all possible incentive-compatible mechanisms, the set of incentive-compatible mechanism equals the set of maximal in range algorithms. So we have an equivalence between these two classes. The problem is that for auction domains, we know that this is not true. We have like algorithms that are not maximal in range, okay, and are incentive compatible. We don't know that they provide a good approximation, but it's still not true that the set of all mechanisms that we care about are maximal in range. Maybe there are incentive compatible algorithms that provide a good approximation and are not maximal in range. Right now, all incentive compatible algorithms that we know that are not maximal in range are silly. For example, I say something like bidder 1 does not get any items, but if his value for 10 items is 10, then bidder 2 is going to get 10 items, otherwise it's going to get 15 items. Okay, so this is incentive compatible, is maximal in range, it's not maximal in range, and is also not doing anything useful. So so this is not great for us. So for a long time, we wanted to prove that the set of all incentive compatible mechanisms that provides a good approximation, that are useful, is maximal in range. We tried to prove it. We put a lot of effort in proving this, but turns out that this is simply not true. It turns out that for every epsilon, there is an incentive-compatible two-player multi-unit auction that provides a 1 plus epsilon approximation, and this auction is not maximal in range. Also, does not run in polynomial time, but this picture that I have here is not true. It's not true that the set of all algorithms that provide a good approximation and are incentive-compatible is maximal in range. So this situation is not true. In fact, we know how the world does look like until under some scalability assumption. We know that for two players multi-unit auctions with 2 items, every scalable incentive compatible mechanism that provides a 2 minus epsilon approximation is something that we call a triage auction. So the world looks like this. The intersection of incentive compatible algorithms and algorithms that provide a good approximation consist only of triage auctions. And we can also do the second optimization step, but now for triage auction and not for a maximal in range algorithm. That is, we can prove that every mechanism that provides an approximation ratio better than 2 for multi-unit auction for multi-unit auction and is scalable, does not provide a good approximation in polynomial time. We do that by characterizing the set of algorithms for 2 players and then somehow scaling up this result for n players and showing that, in the limit, if you wish, triage auctions are very similar to maximal and range algorithms. I'm not going to discuss it here. But the point is that under this scalability assumption, we can prove that there is no multi-unit auction that provide a better than 2 approximation in polynomial time. Scalability just means that we don't care about the currency in which the evaluations are specified. That is, if I measure the values in rupees or in dollars, the algorithm is going to get the same result. If I multiply all the valuations by the same constant, we're still going to get the same result. Okay, so this is what we have. We know to prove it, but under this annoying scalability assumption. Okay. Okay, so what else can we do? How else can we prove impossibility result for other domains? This characterization result for multi-unit auctions was quite hard, and doing it for more complicated things for like combinatorial auctions is not easy at all. So here we're going to think about something that let's call it a direct hardness approach, and we're going to limit ourselves in another way now. Instead of just assuming a general communication model where the players can freely exchange the bits about their valuations, we're going to focus on value queries. We're going to assume that all the mechanism can do is ask each player what is your value for 10 items, what is your value for 15 items, and so on and so forth. Okay, so we're going to, for now, we're going to limit ourselves for these value queries. And the idea is to use something that is called the taxation principle. So what is the taxation principle? The taxation principle tells us that we can think about each incentive compatible mechanism in the following way. Each player is facing a menu, and the menu specifies a price for each alternative, and the bidder just chooses the alternatives that maximizes its own profit. So this is like, I don't know, going to McDonald's, you look at the menu. The menu says, Big Mac $1, Big Mac and Coke $1.5, and you just compute what is your most profitable alternative, and that's the one that you choose. Right? The magic in an incentive compatible mechanism is that each player is facing such a menu. This menu depends only on the valuations of the other players. And still, each bidder is going to choose its profit maximizing alternative. And somehow, all bidders simultaneously choose their profit maximizing alternative, and we don't have collisions. It's not that, I want this bundle and you also want part of this bundle, so we don't know what to do. The magic in the incentive compatible mechanism is that we all choose our profit maximizing bundle, and we all agree about the allocation. So that's like, the interesting part here. So, and the taxation principles tells us that every incentive compatible mechanism can be implicitly thought as doing this process. Yeah. Is it clear, or do I need to explain the taxation principle again?
Aki, could you just run through it one more time? I didn't quite get the taxation principle.
Okay, so the taxation principle tells us the following. We can think about each mechanism, each incentive compatible mechanism in the following way. Each bidder is facing a menu. This menu depends only on the valuations of the other bidder. So if you have 2 bidders, you can think about it as bidder 1 that sends a menu to bidder 2, and bidder 2 simultaneously sends a menu to bidder 1. Each of them is facing a menu. This menu tells you, if you take 10 items, you're going to pay 15. If you take 11 items, you're going to pay 20. If you're going to take 13 items, then pay 51 or something like this. Each bidder just chooses the alternative that maximizes its profit, the alternative that maximizes its value minus price. Okay. And somehow in the incentive compatible mechanism, we don't allocate too many items. Okay, so each of us just took the bundle that maximizes its profit, and we don't allocate too many items.
Okay.
Is it better now?
Okay.
Okay. So now that we have this property, let's try to to leverage it into proving the impossibility result. So let's suppose that this is the menu that is presented to bidder one. One apple gives you a value of $10 for you. Two or three apples, same thing, price of $20. Four for a price of 40, and so on and so forth. Just some arbitrary numbers I put there. And now let's consider the following valuation of for bidder. The valuation is going to be the same as the menu. If he gets one apple, then his value is 10. Two, his value is going to be 20. Three, his value is going to be 20 as well. In this valuation, no matter what alternative he chooses from the menu, his profit is going to be 0. Because the value always equals the price. This is how we constructed the valuation. Okay? So in this specific valuation, the profit is going to always be 0 no matter what this bidder is going to choose. So let's consider changing a little bit the valuation of bidder I. If we just add 1 to the value of this bidder for taking 3 items, then his value is going to be 21. And the profit of this bidder for taking 21 items, for taking 3 items, is going to be 20 minus 20, which is 1. Right? The profit of every other bundle is going to be 0. So this means that the only strictly profitable bundle for bidder 1 is going to be the bundle of 3 items. So the incentive compatible algorithm must choose this bundle by the taxation principle that tells us that each bidder gets its profit maximizing bundle. Now, but this one, we added the 1 to the alternative with 3 apples. We can, put it maybe to the one with 6 apples or something else. The point is that if you just have access to asking, what is your value for 1 item, 2 items, and 3 items, finding the +1 is going to take you a lot of value queries. You basically have to query each possible menu entry for that. Right? So that's the hard task. We only slightly change the evaluation function. The incentive compatible algorithm must, by the taxation principle, must find this mostly profitable item, the one that we change a little bit. And this is a hard task if you only have access to value queries, to asking what is your value for 1 item, what is your value for 2 items, and so on. So this is the basic idea. And we take this idea and we have to extend it to the more complicated settings like some model evaluation. With some model evaluation, we have again a simple maximal and range algorithm that provides a square root of m approximation algorithm and uses polynomially many value queries. And by this extension of this direct lattice approach that we just saw, we can prove that this is the best we can do for every incentive compatible algorithm using polynomially many value queries. So this gives us an approximability here. And this was extended to various settings, randomized mechanism, and so on and so forth. I'm not going to discuss it here. Okay, so this is great, but what are the disadvantages of this direct arguments approach? First, we don't know how to prove impossibilities using this approach for multi-unit auctions that we started this talk with. Also, there are other queries in the world like demand queries or general communication. We can ask other things more than value queries, and this direct lattice approach, we don't know how to extend it to more complicated queries. So we need something completely new for if we want to prove algorithms for multi-unit auctions or for things like demand queries and so on. And this is going to be our third approach, which is going to use the taxation complexity. So what is the taxation complexity? we define the taxation complexity of an incentive-compatible mechanism as the logarithm of the maximal number of menus that may be presented to a player. Okay, let's try to decipher this this definition. I just told you that we can think about every incentive-compatible algorithm as one in which each bidder is presented with a menu. So let's count the number of menus that might be presented to a specific bidder. Okay, so we're going over all possible valuations of bidders 2 to n, and for each possible valuation 2 to n, we see what menu is presented to bidder 1, and we're just going to count them. Now, the taxation complexity is simply the logarithm of the maximal number of menus that may be presented to a player. Why the logarithm? Because we want to be able to point to a specific menu, and this, if the number of menus is x, then we need log x bits in order to point to a specific menu in this collection. Okay, so this is the taxation complexity. Essentially, the number of items, the number of menus that might be presented to a player, the logarithm of the number of items that might be presented to a player. So why do we care about this taxation complexity? Because informally, it turns out that the taxation complexity characterizes the communication complexity. So in every incentive compatible mechanism, if you want to determine the communication complexity of the mechanism, just count how many menus it presents to the players, take the logarithm of this number, and you have the communication complexity. In other words, incentive compatible mechanisms are not much than protocols for exchanging menus. Okay. What we're going to see next is actually a counterexample to the theorem. I told you this is just an informal result. So we're going to see a counterexample to the theorem, which will help us give the actual conditions that we needed in order for this statement to hold. Okay, so let's do this counterexample. So I claim that there is an incentive compatible mechanism in which the taxation complexity is exponential in the communication complexity. What is this example? This is going to be the VCG algorithm applied to two-player multi-unit auctions, where the valuation functions exhibit decreasing marginals. Okay, so maybe the first item has a value of 100 for me, the second item has a value of 150, then 140, then 160, then 165. So the marginal contribution of each additional item decreases. Okay, so we're going to think about VCG applied to two-player multi-unit auctions when the valuation exhibit decreasing marginals. I claim that in this case, there is a small communication. That is, the communication complexity is polylogarithmic in M. This is because in multi-unit auction with decreasing marginals, it's actually very easy to find the optimal location. It's just binary search. This is actually, I always give this to students in my class. It's a nice exercise. It's not very hard. Basically, you just need to find the marginal. Okay, you can think about it offline. Offline, it's not very complicated. So you can quickly find the optimal solution in this case. However, I claim that the taxation complexity in this case is quite large. To see that, just pick some player with valuation V1. The price of bundle S in the menus is presented to player 2 in the VCG mechanism is, I'll just tell you what it is. It's V1 of M minus V1 of M minus S. And as you can see, the price of bundle S is completely determined by the value of M minus F. Okay. And this means that the number of possible menu is simply the number of possible valuation, because a change in one value changes the menu. So we take the logarithm of this, and we get that the taxation complexity of VCG is log the number of valuations. And now, just by quick counting, the number of multi-unit auctions, valuations with decreasing marginals is exponential in M, and we guess that the succession complexity, taking log for something exponential, is polynomial in M. Okay, and we got that the succession complexity is exponential in the communication complexity in this example. Okay. In general, we can prove the following. That's the correct condition for the informal statement that we just told you. If we have an incentive-compatible mechanism for combinatorial auctions or multi-unit auctions, and we have general valuation or sufficiently rich set of valuation, then the succession complexity is at most the communication complexity. The other side that tells us that the communication complexity is at most polynomial in the succession complexity. It's easy for two players and it's more challenging for more. But basically, we know that the succession complexity for rich enough domains is essentially equals to the communication complexity. Okay, so how can we use this statement in order to prove impossibility result? Impossibility result, this is the focus of this talk. We can use two different approaches. One is straightforward. If we know that the communication complexity equals the succession complexity, then let's just prove that the succession complexity of every incentive compatible mechanism that achieves a good approximation ratio is exponential. And this will give us that the communication complexity is exponential as well, and will give us the impossibility result. The other one is a little bit more delicate. It's by showing that if we have a two-player alpha approximation incentive compatible algorithm, we can transform it to a two-player alpha approximation simultaneous algorithm with the same communication. Basically, this algorithm is not incentive compatible. So again, we start with a two-player alpha approximation incentive compatible algorithm, where this algorithm might be iterative. The players might exchange bits and ask questions each other, and we can transform it into a simultaneous algorithm where there is only one round where both players simultaneously speak. They speak essentially the same number of bits as they spoke in the incentive compatible algorithm. And this algorithm provides an alpha approximation. Okay, and again, this simultaneous algorithm is not incentive compatible. So what we did here is we got rid of the incentive compatibility of the algorithm. Now we are in a domain where we only have to study simultaneous algorithm using standard communication complexity algorithm, no more game theoretic argument. And that's good because we have more chance of proving impossibility results using standard tools that have been developed for years in communication complexity, rather than complicated game theoretic settings that say something about the incentive compatibility of the mechanism. Okay, so that's the approach, and indeed, in a great result, and I assume that you identify at least some of the authors in this result. So they've managed to prove that every two-player simultaneous algorithm for something that is called XOS valuation, that is in particular for some model evaluations, that guarantees an approximation ratio better than something as an exponential communication complexity. This 1.34 is a little bit larger than 4 over 3. 4 over 3 is what we can do with polynomial-time algorithms that are not incentive compatible. So this proves for the first time that there is a separation of low communication incentive compatible mechanisms and polynomial-time algorithms. That is, if you insist on incentive compatible algorithms, now we finally know that you have to pay something in the approximation ratio. Okay? Questions? Okay, so this is great, and there are some other results that following this result that were managed to prove some separations in other domains. Note that this separation is really small. All separations that we know are actually quite small. We still don't know how to do it for multi-unit auctions, for example. We still don't know how to prove such gaps for multi-unit auctions. We still don't know to prove large gaps for some other evaluations and combinatorial with some other evaluation and stuff like this. So there's still with general number of bidders. So there's still a lot of work to do this, but at least we've managed to prove for the first time a separation between these two classes. Okay, I wanted to show you a proof that the taxation complexity is at most the communication complexity. The proof is actually quite nice, and it's only like 2 slides. But I see that I don't have much time for this, so let me just keep this. Although the animation is really nice here. And let me quickly summarize what we discussed so far. We discussed method for constructing computationally efficient incentive compatible mechanisms, basically maximum and wage mechanisms. We don't have much other tools beyond maximum and wage algorithms. Then we discussed methods for proving impossibilities for computationally efficient incentive compatible mechanisms. We discussed the characterize and optimize approach. First, characterize the set of all possible mechanisms, and then prove impossibility results for this set using computer science tools. We discussed the direct hardness result, where we use the fact that it's hard to find the profit maximizing bundle in the menu, which contradicts the taxation principle. And then finally, we showed that mechanisms are not much more than protocols for extending menus. And basically, we showed that protocols for extending menus might need more communication to obtain some approximation ratio than if we think about general algorithms that are not restricted at all, except that they're running polynomial-time. That's all. Thank you.
Yeah, so for multi-unit auctions, what is the best lower bound that we have?
So with the best lower bound, nothing. We don't know any separation. So you can do like 1 plus epsilon in polynomial-time, and then for non-incentive compatible algorithms, I don't know that if you add if you insist on incentive compatible algorithms, it takes you I don't know 1.01. I don't know that. If you can prove this, this will be really great.
But we know that if we insist on MIR mechanisms, the lower bound is 2. Is that correct?
Yeah, we know that maximum and range algorithms cannot give us more than 2 approximation in polynomial-time, but for general incentive compatible algorithms, this is a major open question. I just don't know how to prove any lower bound for this.
Do you want to say anything about randomized mechanisms? Like, can we for multi-unit, do they give us a lot more, a bit more? Or?
Okay, yeah, good question. For this talk, I focused only on deterministic mechanisms because I wanted to focus on impossibility result. Situation for randomized mechanisms is actually much better. For multi-unit auction specifically, okay, it depends on the type of the random of the randomization that I allow you, the type of incentive compatible mechanism. For something that is called truthful expectation, we actually know how to get an FP task for multi-unit auctions in polynomial-time. That is, there is no gap between this kind of randomized mechanisms and non-incentive compatible mechanisms. If we use like stricter notion of incentive compatibility, like universal truthfulness, then we don't know if there exists an FP test, but we know that there is no P test. We don't know if there is an FP test, but there is a P test. So there is like a gap between a P test and an FP test, but between what we know. So that's what we know. For combinatorial auction in general, like for combinatorial auctions with some model evaluations, there are like really great results recently that proves like that with randomization we can get a log-log approximation ratio compared to a constant that we can get if we ignore incentive issues. So there is still a gap. if you ask about proving impossibilities on the power of randomized mechanism, then we don't know to prove any gap as far as randomized mechanisms are concerned. So, it took us a lot of time to prove impossibility for deterministic mechanisms. Proving impossibility on the power of randomized mechanisms, this is really something that we're not sure how to do for now.
And okay, last question. So, and of the various questions you mentioned, like, if I asked you to pick one out, which would be a good candidate for, being reasonably solvable and interesting, do you have a favorite question, or do you have a?
So I have a favorite question. I don't know if it's necessarily the most easier one to solve. But my favorite question is actually multi-unit because it's so simple and for example, for some model evaluation, sometimes we have a lot of trouble in constructing some model evaluations. It's a complicated object. Things like some model evaluation. Multi-unit auctions, they're so simple. So somehow let you focus on the aspect that we don't know rather than on aspect that people know to do quite well, like constructing complicated evaluations. This is all good in theory. In practice, I haven't managed to prove a separation. So why would you listen to me?
More questions? Okay, all right. So in that case, thanks, Shahar. Thanks for the.
Thank you.
Thanks, Shahar. So I'm going to close the stream now. I'm going to close the Zoom session now. Start. I don't know what happened. I don't think it's. Okay. Start here.